Okay, so we'll go ahead and get started here. Thanks everybody for joining, especially right after the short lunch break that we all had. So take a second to get settled. I'll start slow. So I'm Patrick. I'm a principal engineer working at Amazon. Most of my work focuses on distributed systems for business intelligence at Amazon. And in this case, we're going to be talking about a particularly large-scale migration, which we've completed part of and is still ongoing, from Apache Spark over to Ray. And as far as the open source side of my work goes, I'm also a member of the Ray project. Maybe some of you have heard about it. It's mainly focused publicly on distributed systems for machine learning pipelines. But this is an interesting use case. We're actually using it at very large scale for primarily data processing pipelines and helping transition those data processing pipelines into mixed purpose data processing and machine learning pipelines. So let's go ahead and get into the syllabus here, kind of what we're going to be going over for the next 40 minutes or so. We'll go through an introduction to the work that we're doing here and why we're doing it. We're going to talk about this so-called compaction problem that we have. Those of you that work with other catalogs like Iceberg or Hoodie may often know compaction via the words they use, copy on write or merge on read, in order to rectify the results of writes you do to your data sets. So that's a subset of what we do in this problem called compaction. And we'll talk about us migrating off of Spark as a solution for this problem historically at Amazon, some of the results we've achieved, future work, and maybe give you some links to get involved and help us out here in open source with the ongoing work if you all are interested. So first for the introduction, we'll go over the journey in open source and at Amazon that we've been through from a historic data warehouse based on Oracle over to more of a lakehouse style architecture today. We'll talk a little bit about what business intelligence is, a brief history of business intelligence to Amazon, and what Ray is and why we selected it for this particular problem. So first, an intro. Some of you that are familiar with the space may already be familiar with some of the terms that are put up here. So data warehousing is where a lot of us started and where Amazon was when I first joined back in 2016. Amazon was actually running a very large scale Oracle data warehouse for managing their business intelligence data. And data warehouses have historically followed this structure of having coupled storage and compute over highly structured data. And they have some nice advantages, namely ACID compliance. For those of you that, again, work in the space or work in databases or may be familiar with ACID compliance, it's a very important property here. It stands for atomicity, consistency, isolation, and durability. And for those of you that maybe aren't so familiar with this concept, it's basically what keeps all of the transactional writes you do to these databases correct and consistent. Make sure you don't do like partially committed data or that you like violate uniqueness constraints of your table. It keeps your data correct, consistent, well organized for the most part. So a very important property. Data warehouses had it. And one thing that they didn't have, though, was historically the ability to scale their storage independently of their compute, the actual queries that you would run over the data that's stored. So thus we entered the data lake realm, and that provided basically scalable raw data storage and retrieval using very primitive systems or seemingly primitive. They're still used very much today still, but Hadoop came out in the early days there, and HDFS, and then various cloud storage solutions. We have S3 and Azure Data Lake Storage, and GCP provides their own cloud storage solutions. But the main problem with data lakes was they didn't provide much organization for your workloads. So in the early days of data lakes, I often think about it like the dark ages of Amazon business intelligence, there wasn't a lot of structure, and you heard a lot of kind of cynical comments about them degrading, rightfully cynical, frankly, into data swamps, right? Because people, had abandoned ACID compliance largely in their haste to decouple storage and compute and get into data lakes. And so then data catalogs started emerging and started bringing some structure back to these data lakes. Hive was one of the first ones, and it had some very simple concepts of structuring your previously unstructured data, like organizing them into partitions. And your partitions were simple and easy to understand because they were just the directory paths. And you put your partition name and the values that it corresponded to into your directory path. Kind of cool, kind of easy to understand, but it had certain limitations. You can't necessarily put every value in a valid directory path. So other systems like Iceberg and Hoodie, and then later even Nessie and Delta Lake, started to build additional metadata on top of these data lakes to start to give you some of the primitives you needed to get ACID compliance back in these systems. So they started to provide you with schemas and consistency enforcement mechanisms to make sure that when you're doing a write to a table that has a schema, you're not violating the schema. They started giving you atomic transactions again. So we were starting our journey back to ACID compliance, it seemed, but with decoupled storage and compute. And then the lakehouse concept was introduced. I think the term was first coined by Databricks around like 2021 or so. And they kind of said, hey, it doesn't have to be one or the other. You don't have to decouple your storage and compute and then throw away ACID compliance. You can decouple your storage and compute and still keep ACID compliance for the most part. And so business intelligence at Amazon is largely focused on spinning this so-called business intelligence flywheel that we have here. Basically collecting business insights, making data-driven decisions from those insights, improving operational efficiency based on those data-driven decisions, which leads us to collect even more business insights. And at a certain level, the whole thing gets a little bit meta. We apply business intelligence to the business intelligence organization itself to see how well it's operating as a business unit at Amazon. And something kind of relevant as we get into our talk here, I briefly mentioned earlier that Ray's largely focused on machine learning. We're also focused on decision evolution at Amazon, and I think broadly across the industry, from this initial phase where we were all human in the loop making manual decisions based on data analysis, to eventually going to human in the loop supervised decisions with some assistance from machine learning, and then eventually going into fully unsupervised decisions where it's safe to do so, where we try to get humans out of the loop for making these decisions. So the organization that I work in at Amazon provides a centralized hub for business intelligence data for all businesses at Amazon to connect to write their business intelligence data and to read it back and to understand and to glean these insights, whether manual or automated, about how their business is running. And so a brief history of business intelligence at Amazon, at least as far as I've been there. So like I said, I joined in about 2016. And at the time, we were working on a petabyte-scale Oracle data warehouse deprecation campaign. During that campaign, we migrated about 50 petabytes of Oracle data warehouse data to an S3-based data catalog. So all the data files went in S3. We built metadata cataloging layers on top of them to bring some structure to it. And we successfully decoupled our storage and provided initially Amazon Redshift and Apache Hive-based compute running on Amazon EMR on top of our storage layer. And there's a fun post there when we publicly announced the deprecation of this Oracle data warehouse to be complete, from our now CEO, Andy Jassy, and CTO, Werner Vogels, noting that it was one of the largest, if not the largest, Oracle data warehouses in the world. And it was quite an exercise to deprecate that beast of an Oracle data warehouse. Would take more than 45 minutes just to describe that alone. And so from 2018 to 2019, kind of freed from the shackles of storage that cannot scale independently of compute, our data lake, becoming a catalog, quickly grew to exabyte scale from its prior petabyte scale, which was a bit of a blessing and a curse at the same time, because we didn't have all these lakehouse trappings in place immediately to give good ACID compliance to everything that was going on. But we did have a decent model for bringing your own compute to the data catalog that we built. And so the diagram on the right there kind of shows how it works. Data producers would load new deltas of data. So these are basically S3 files to insert, update, or delete into namespace tables in this catalog. Consumers would have their own AWS account. It would synchronize and merge all of these deltas coming in as inserts, updates, and deletes. And then they'd query it with whatever their favorite compute framework was. So it's kind of a federation campaign, like, hey, guess what? You can now compute over it with anything you want to. Sounds good for the customer. It was horribly complex, as you might imagine, to actually make this happen and to make all these different compute systems consistent with each other and, not just crash outright when they're trying to read something that they didn't write. And then one of the problems we soon had was, well, if you're just appending to the table over and over and over again, infinitely, the tables eventually grow too large for any of these compute frameworks to consume and merge and rectify what they're reading at read time. So what do we do about that? Well, we turn to Spark, as it were, to do this log structure merge-based change data capture log compaction. So there's a very simple illustration of it on the right for a pure append table, which is probably easiest to understand. In this table, it's just logically saying, hey, I've got two little tables there saying 1, 2, 3 ABC, 1, 2, 4 DEF, and I'm just appending them to each other. So instead of having two tiny files with 3 rows each, I get one bigger file with 6 records in it. So now you just read one small file instead of 2 small files. Okay, that's a very simple version of compaction to optimize reads. It gets a little bit more complicated when you have merge keys, because now you have to deduplicate the data. In this case, the merge key is column 1. So we're finding all matches on column 1 and keeping the values for the latest versions of column 1 from the other columns. Well, finding duplicates is a simple enough problem in theory, but it turns out to get a little nasty when your data starts growing to petabyte scale and beyond and can no longer fit on a single node. So then enter 2019 to 2023, where we started working to find a substitute that could be more efficient than Spark at this problem, more scalable, more resilient to out-of-memory errors. We had a long laundry list of problems we wanted to solve, ideally. And we ultimately settled on Ray. And this was the very early days of Ray, before they had so leaned into the machine learning and generative AI space, where they're generating and developing most of their high-level APIs these days. Because Ray at its core is a very general-purpose distributed compute framework that I'd like to argue could be good at almost any distributed systems area where you decide to magnify and focus its attention. And we focused it initially on this dataset compaction problem. And so the diagram on the right shows how things got a little bit more complicated at first. We now had a Ray compactor shadowing a Spark compactor, and we were doing a lot of data reconciliation work to make sure that query engines would see equivalent results when querying results produced by the two of them. And we also had a data quality service that would collect a bunch of stats about the data and call something out if anything looked glaringly wrong between the dataset produced by Ray and the dataset produced by Spark. And now here in 2024 and beyond, we're actually going into this realm of Ray exclusivity, which basically involves migrating all table queries to the Ray compactor's output. So all table consumers are now consuming from Ray exclusively. And then once that's the case, we just shut down Spark. And now we can finally start getting some of the cost back that we'd sunk from just running them in parallel before. And again, some of you may not be too familiar with what Ray is, so a quick introduction to it and why we chose it. Ray is a Pythonic framework, or mainly its flagship APIs are Pythonic because, again, it's focused on integrations with the data science and machine learning communities primarily to provide distributed Python APIs for machine learning, data science, and again, general purpose workloads. We had started looking at it not only for compaction, but because we also had a lot of data scientists and machine learning engineers who were having these long-standing troubles with integrating their machine learning pipelines with our data catalog and their data science workloads with our data catalog. If any of you have worked in this realm and you're using pandas on a single host, it's all great until you tell pandas to go out and read some terabyte scale data set. Then it doesn't go so great. So Ray was starting to look promising at solving some of those problems. And the more we looked into it, the more we thought, hey, maybe we could solve the compaction problem too. We found the APIs that provide to be very intuitive. Basically, you take any old Python application that you have that could be parallelizable. You put annotations on it for tasks, which are distributed functions, and actors, which are distributed classes. And you can now start deploying that code to an arbitrarily large cluster, and it'll manage a lot of the cluster scaling for you. Like you run it on AWS, it'll automatically request new EC2 instances as it needs them and automatically remove them from the cluster and return them so you don't continue paying for them as it doesn't need them. And one of the important points here is that we thought it had the potential to be a unified framework, to potentially be a unified distributed compute substrate that would actually run all of the mixed purpose data processing, data science, and ML pipelines that we had on just one compute framework. So it's kind of a North Star goal that we had there. And so let's get into the compaction efficiency problem a little bit here that we had in particular. We'll start with a definition of efficiency. So one of the oldest definitions of efficiency arguably comes from physics. We'll say that's just useful energy output from some system divided by the energy you put into that system. And in computing terms, we'll say that's useful computing output divided by the computing resources you input into it, number of CPUs, RAM, etc. So in other words, the more useful work you do with the same resources, the more efficient you are. So if we give a simple example of a system reading 2 gigabytes a minute of some input data set with 1 CPU and 8 gigs of RAM, and system B has the same exact resources but can do 4 gigs a minute with the same data set, we'll just say system B is twice as efficient as system A, all other things being equal. And let's also understand how this is relevant within the realm of Amazon Business Intelligence pricing. We set up a pricing model internally. We have tens of thousands of consumers who are querying our catalog across all of Amazon's businesses day in, day out. And we have them pay per byte that they consume historically from our data catalog. And we basically divide the administrative costs of maintaining that data evenly across all the consumers who are benefiting from us maintaining it. And thus everyone winds up being charged the same normalized amount per byte that they read. And the primary administrative cost going into their bill is this compaction thing, this whole process of globbing together all the appends that come in and finding duplicates and merging upserts that come in to the catalog. So we kind of already went over what compaction is, what its inputs and outputs are. Inputs is a bunch of deltas containing inserts, updates, and deletes stored in files like parquet files or delimited text files, let's say. And output is then a set of S3 files with all the inserts, updates, and deletes just magically applied for you. It figured it all out, and it creates a read-optimized version of the table. And it's very expensive how we were running it because we were initially saying, hey, we'll just run it after any write to so-called active tables in our Exabyte-Scale data catalog. So not all tables are considered active. They go into various life cycle states. So that helps us manage it a little bit, but that again requires human in the loop. Somebody say, hey, I'm not using this data set anymore. You can deprecate it. Don't run compaction on it anymore. People usually aren't responsible enough to always deprecate or mark their data set status inactive when they're not actually using it anymore. You usually have to bother them about that. So, best effort. And like we said, this actually incurs a very large compute cost to merge the input and a large storage cost to now write the output because you're creating copies of all these files. You merge 2 tiny files into 1 larger files. Now you got 3 files in total. And you got to do garbage collection over the old files. But, it's important. Overall, it's still cheaper and it still keeps reads functioning than telling all readers to always do the same thing every time they read. So it's caching. And it also enforces critical security and compliance policies like GDPR. Like, hey, some customer popped up and said, you got to delete all my data from your system. Say, okay, we'll go find it and delete it. Compaction is the thing that actually deletes it. And this gets us into the compaction money pit problem. So once again, consumers pay per byte consumed, and the primary administrative cost is compaction, and that's our Spark cluster over there, doing compaction like we illustrated earlier. And so we just kept throwing money at Spark, and the data sets grew in size, and we just kept throwing more money at it. Not the most elegant solution to the growing problem. And so we started looking at alternatives. Enter the Spark to Ray migration. So some key milestones by date. This has been going on for a while. We'll probably still, like I say, continue to go on for a couple more years out of that. Back in 2019, we met with a team at UC Berkeley who were founding the Ray project. There's now a company behind it called Scale. Some of the co-founders are the co-founders of Databricks as well, and people who worked on Spark from UC Berkeley. So we investigated this new compute framework with them, said, hey, well, what have you all been up to post-Spark? And we found out about Ray. And so we started investigating it and benchmarking it, doing all kinds of analysis, and we threw the compaction problem at it too. And we saw some promise in being able to solve the compaction problem more optimally using Ray. And so we came up with this flash compactor algorithm design, which is now published in open source. We have a project called DeltaCat, which I'll talk about later. We have a long PDF there describing our initial design for this on Ray that use some of the unique features of Ray to speed up this workload end to end. And then we came up with a proof of concept code implementation of this design. Like, okay, it looks cool in theory. Does it actually work when you code it? Or is it horribly inefficient? Proof of concept looked pretty good, actually, against the test data sets we baked up. There were areas for improvement, but we worked with the Ray community to improve them over time and got better and better. And then we had enough faith in it in 2021 that we made a full-on kind of serverless style Ray job management system internally. So, it's cool to just run one test on your laptop in your own AWS account against some petabyte-scale data set. But what if you have to run thousands of petabyte-scale jobs day in, day out? You need more sophisticated job management. So we designed that and implemented that in 2021. And then 2022, we put it to an early test by saying, hey, let's figure out if you can use Ray's diverse tools of data science and ML to do better data quality analysis on our existing data catalog. We have a lot of mysteries there about the quality of the data. So let's see if Ray can help us with that. And it did. And then that also became a prerequisite for, we use that same data quality analysis framework when we started shadowing the Spark compactor output with the Flash compactor output on Ray. So we could turn that data quality analysis framework that we built earlier onto the results of Ray and Spark and say, hey, DQ checks all look the same. Great, move on. And 2023, latter part of 2022, we did start shadowing Spark in production. 2023, we started migrating consumer queries from querying Spark to consuming the Ray compactor's result sets. And 2024, where we are today, we're gradually shutting off Spark as all consumers on many of our largest tables that Spark has historically been struggling with are being migrated whole scale to Ray without problems. And some of the challenges that we faced with this whole migration, well, correctness was a big one, and even defining correctness is an interesting challenge. You can kind of get like this ivory tower stance towards what is correct and what is not, and stand on a high horse and tell all your customers that they're wrong, and that the results that they're seeing today are not actually correct, but usually they just want, what they've been historically getting, because anything else will start to disrupt things in ways that you can't possibly anticipate across thousands of customers. So that ultimately meant correctness equals backwards compatibility with whatever Spark said. Ray wasn't really designed for that, so we had to do it ourselves. And a lot of that came into specifically underneath Ray, Spark and Arrow type system differences that we had to rectify across the board. And then, budgeting for deferred results was a big problem. You have to convince your management and everybody holding the purse strings at your company that, hey, guess what? Your costs are actually going to go up to run these two systems in parallel for an undetermined amount of time before they start to go down. And we just hope that they will go down. We have to continue to deliver you proof of concepts that show that, there's still light at the end of the tunnel. Fortunately for us, the largest 1% of tables, or maybe unfortunately for Spark, incurred about 50% of the cost. So we have this long tail of super large tables in our catalog that are disproportionately represented in the compaction problem set. So we could turn Ray's focus on those first. And then operational sustainability, just managing clusters, providing that serverless cluster management experience takes a lot of money. Making them scale better, solving scalability constraints at the individual cluster level on Ray's side is also ongoing work in progress. There's always upper limits on how large you can grow your cluster before some bottleneck inside of your cluster management system starts to drag it down and just maybe outright crash in some cases. And then, we had a lot of regressive data sets to deal with, which for the most part deals with some data sets are streaming style, and you've got to stitch together tons and tons of tiny files that are constantly arriving, while others have disproportionately large clusters writing some ridiculous like terabyte-scale single files, which now you have to split up. So those were some of the main challenges that we went through. Not a comprehensive list. One interesting challenge in particular to focus on was the customer experience that we wanted to get here on a seemingly paradoxical goal around maintaining this customer experience of completing an exabyte-scale compute framework migration somehow invisibly, so that customers never even know that this is happening behind the scenes. They're just writing tables and reading tables all day. There's no Ray, there's no Spark. So that's all they want to know. I read a table and you just give me the results. But there's one tricky part of that problem. They need to know how complete the table they're consuming is. If any of you are maybe familiar with Google Data Flow and how they think about these things in the streaming world and how Flink, inspired by that, thinks about it. There's things like event timestamps and watermarks. Basically, we're talking about the same thing here. All these tables had a completeness watermark. Hey, your data is complete as of today. But Ray and Spark, Ray's generally completing faster than Spark. They don't have the same completeness signal. They don't have the same watermarks. They don't have the same timestamps. So how do you keep it invisible? So yeah, what are we going to tell our customers? Well, as it turned out, we didn't have a solution to that problem with our existing system. But it wasn't a total paradox. It was just our existing system that was the problem. But this is also why the migration took so long, because we now also had to build dynamic routing, as we called it, per table consumer to get the right answer. So now the answer to how complete is this table isn't as simple as just looking at the table, because now there's multiple tables. We have to know, well, who are you and which one have we routed you to? Okay, now I have that additional context and I have an additional service whose sole purpose in life is to provide that answer. Like, who are you? Which variant of this table are you consuming? We can now say, yes, I know how complete it is, and it always depends on who's asking. From the web page you're looking at that shows you a little bar to your automated system that decides when your job runs. And we made various unfortunate concessions that we didn't want to make when we started in our ivory towers at the beginning of this project. Like going back to correctness equals whatever Spark used to do, as far as our customers were concerned. This meant that we initially wanted to write with a bunch of fancy new features from the latest Parquet format specification, but wound up regressing to Spark flavored Parquet 1.0 that was missing all these features, just because, that was par for the course and we didn't want to disrupt the status quo because it would set off unknown chain reactions downstream of us. And this also has lined us up for a subsequent migration back up to a newer Parquet file format spec, which is now currently ongoing. And then we initially thought we'll have one great unified implementation of compaction that will solve all of our problems. It turns out there's probably no single implementation of this thing that is actually optimal across all data set and cluster hardware variations that you might throw at it. So we're looking at a world where we already have two different implementations sitting in open source right now, specialized at different types of tables and different balances of efficiency versus scalability that you might want to have. And we're probably going to have even more implementations going forward. But again, it'll probably be some sort of dynamic routing layer in front of them all in the future where somebody just says, hey, compact my table. And we'll try to make an intelligent choice. Oh, okay, compactor 3 of 10 is the right one for that table. And, we're always balancing this ROI of maintaining versus discarding an implementation. Maybe if we don't dynamically route any compaction jobs to compactor 4 of 10, eventually it gets nixed from the list. We also had to make a lot of manual memory management concessions because with Ray's default object store, how it manages memory on the cluster, it's pretty difficult to predict at either an individual task invocation time, which is like a single instance of a distributed function, how much memory it will need to do the job that it has at hand, or how much max cluster memory you might even need for the peak scaling load of an individual job. And we ended up implementing our own garbage collection mechanisms. We didn't want automatic reference counting and garbage collection that came with Ray. It didn't wind up working very efficiently for us. We just said, hey, you know what? I'll tell you when to collect the garbage. I know when I'm done with it. And so some of these lessons learned, I already went over, like correctness. Yeah, your customers define correctness. Listen to them. You have to meet their requirements and their needs, not like the ivory tower ideals you might want to impose on them. And operational sustainability, when you're dealing with things at Exabyte-Scale, Murphy's Law always comes true. You can't just say like, oh, what are the odds of that happening? Especially if it's like, hey, 1 in a billion on a per record level is going to happen multiple times a day in this system. So, and then regressive data sets, you want to find them and know about them as soon as possible. So start testing on production data as soon as possible. And just because your code coverage looks good, hey, I got 100% code coverage and branch coverage, as we all know, doesn't mean you actually covered all the corner cases and edge cases. You're going to only get those vetted by testing against real production data too. And at scale, an interesting observation, QA and telemetry converge. You can't possibly QA every case. But if you have good metrics, you can retrospectively understand at least what happened and proactively understand when something bad is about to happen. So let's go into results a little bit. These were previously published in AWS open source blog post. This is looking at from January to March of this year, what we call EC2 instance minutes. So how many minutes an equivalent EC2 instance executed on Spark and Ray for a gigabyte of data to compact. And we can see here Spark requires about 0.576, a little more than half a minute on an equivalent EC2 instance to Ray to compact a gigabyte of data, whereas Ray is only taking 1/10 of a minute. So we're getting about 82% efficiency gain in practice, in production, compacting and merging all this data on Ray versus Spark. And this was sampled over about a little more than an exabyte of input S3 Parquet data in this case. So pretty big result set. Ray compactor memory utilization. This is something I wasn't entirely happy with. Yeah, I think the team's entirely happy with it. It's okay. Could be better. We're typically using about 55% of the memory of clusters that we throw at Ray. So it means, our efficiency gain versus Spark could be better if we get this up to like 80%. There's a certain threshold where maybe if you're over 90%, you're walking on thin ice, dancing without memory errors. But I think it could be better than 55% on average. So we're still working on improving that. I don't have any new updates for either of these two graphs since January to March of this year. These trends have largely continued. Our memory utilization is still about in the 50 to 60% range. These are large clusters, though. Average clusters walking around with 36 tebibytes of memory. So. And this is something we did improve. You see a very obvious trend here, back when we're looking at October to February of this year, of reliability. Ray's reliability was lagging behind Spark here when we took this shot. It was an area of improvement where Ray started out back in October at 85% reliability. Not great. That's a lot of operational overhead to recover from failed jobs, and retries will start of failed jobs, even if automated, will start to burn into your cost advantage. It doesn't matter if you're better if you take 4 shots to actually get the job done. So we focused on improving that, and we ended this chart at saying, hey, our average for 2024 was at 99.15% versus Spark's 99.91% average first compaction job success rate on the same tables. Well, now this looks a lot more chaotic, but it's because the bottom of that is 97, the top of that is 100. We have got a much tighter band of reliability on Ray here, and as of July, we released successive improvements that have consistently brought it up over 99.5%. That little downtrend at the end there is worrying me a little bit, but hopefully we'll just see that bounce right back off. But yeah, our Q3 and Q4 average has been 99.68%. Not quite up to Spark's 99.91 on these same jobs, but, it's a promising trend. And I think we're in enough control of it that I think we can get there and hopefully surpass Spark maybe Q1, Q2 next year. A few fun key production statistics. We run over 25,000 jobs a day here in October. We provision over 1.5 million EC2 vCPUs a day. We merge over 40 petabytes of data every day. Our cost efficiency, the spot R6G EC2 instance average is 59 cents a terabyte. For comparison, the Cloud TerraSort benchmark world record, also held by Ray, is 97 cents per terabyte. So we're beating the Cloud TerraSort cost record here on data merge, at least. A little bit of a different problem, but I think it's still impressive. And projected annual savings, we're looking at over 220,000 EC2 vCPU years of computing time saved annually. If you're an ordinary external customer of EC2 on-demand instances, that equates to saving about 100 million a year on this problem using Ray instead of Spark to do the exact same thing for all your writes to, I don't know if you're writing to Hoodie, Iceberg, whatever. And so some fun facts I'll try to go through quickly. These might not be so fun if you're maintaining the code. all of our internal production data catalog APIs go from Python to Java. Amazon has a huge internal Java code base, Ray's Python native. So we had to make a bunch of shims to make them work together. And most of those are built on top of Py4j. Now, we spent a lot of time stabilizing our dependency on Py4j, but I think it's amazing that actually we haven't had a single big event in production that's actually been caused by Py4j. It's just a pain to maintain Python to Java links. But you can do it if you're careful, and it won't kill you if you're careful. And all of our production compactor code that we run day to day is actually checked into the open source DeltaCat project, like the actual algorithm and the code that runs against our catalog. And so that all the rest of you can start using it on your own tables as well, we first started testing it and porting it over to Iceberg as well. So that's actively undergoing testing and development right now. So hopefully we can give that to you guys soon. And if you'd like to help, it's a little hard right now, I think, until we at least get it working on Iceberg so that, you can reproduce these things in your own environments. Yeah, let us know. So a quick conclusion here. Should I start migrating my Spark jobs to Ray? Hey, this looks great. I'm going to take all my Spark jobs and put them on Ray today. Well, not so fast. Spark's still more general and feature rich for data processing abstractions. There's no general solution for Ray SQL. There's some Ray ecosystem projects like DAF that provide SQL that happens to run on Ray, and it's getting better. But Spark's way more feature complete than Ray today. And there's no paved roads to translate all your Spark applications to Ray native equivalents. And there's some things like RayDP that will run your Spark jobs on Ray, but it's not magical. You can't just throw a Spark job written for Spark on Ray and expect to get these types of performance gains. It doesn't work that way. They tend to probably be less performant. That's because, they're taking an execution plan made for Spark and trying to just fit it into Ray. So we're saying, don't just start trying to throw all your Spark jobs onto Ray today. And so I think the key takeaways here is that, Ray core is flexible enough to let you craft very optimal solutions to very specific problems like this that you might have. And so if you can focus on a particularly onerous and expensive problem that your organization has, maybe you're running it on Spark, maybe you're running it on something else and saying, hey, algorithmically we could do better than what's happening. That's probably a good area if your business is willing to invest with you to turn Ray's magnifying glass onto that problem and saying if you can make it better, if it's important enough to you. But there is a good paper out there written by the people who set the cloud TerraSort benchmark called ExoShuffle. It shows that in general, Ray does have the potential to do general purpose MapReduce jobs actually more optimally than Spark. So it has the potential to do world-class big data processing, but realizing that potential is a lot of work. So future work really quickly. Briefly mentioned it, but we maintain the DeltaCat Ray ecosystem project. We're actively working right now on integrating our compactor with Iceberg on DeltaCat on Ray. And so this should improve your Iceberg table copy on write and merge on read efficiency and scalability, hopefully in a way kind of equivalent to what we just expressed here. It'll also really help you if any of you are writing Iceberg tables using Apache Flink and then trying to read them back with Spark or something else. It should really improve that process a lot. We'd like it to be available for you to use in early 2025. And so we're running a lot of internal tests to verify correctness, stability, and efficiency before we say, hey, everybody come in and start maintaining your Iceberg table for this. But in the meantime, we work with some open source partners on the Adapt open source project who will let you do local distributed Iceberg table reads and writes using Ray as well. So if you're interested, they're one of the best solutions I know of right now for using, Pythonic distributed mixed purpose data science and ML workloads and doing data processing at scale on Ray with Iceberg. So thanks everybody. You can find me anytime on the Ray community Slack. That's my handle there. Feel free to visit us. It's very unadorned right now, intentionally, at the DeltaCat project homepage. But you now know a little bit about what's going on there under the covers. And you can read more about this case study that I just told you about on the AWS open source blog where we published about it previously, I think just a couple months ago. So thanks everyone.